Hello viewers. In this session, we talk about the method of Lagrange multiplier. So the method of Lagrange multipliers is a mathematical optimization technique which was introduced by mathematician Joseph Louis Lagrange in the late 18th century. It is used to find the maximum or minimum value function subject to an equality constraint. So the method is based on the observation that if we want to maximize or minimize a function subject to some constraint, then the gradient of the function at the optimal point must be orthogonal to the constraint surface. In other words, the optimal point must lie in the surface of the constraint. The Lagrange multiplier method introduces a new variable that we call the Lagrange multiplier, which represents the rate of change of the objective function with respect to the constraint. So by considering the Lagrangian, we can find the optimal point that satisfies both the objective function and the constraint function. So the Lagrange multiplier method has a wide range of applications in physics, engineering, economics, and many other fields where optimization problems arise. It is often used to solve problems in constraint optimization, such as finding the shortest path between 2 points subject to certain conditions, or optimizing a manufacturing process subject to resource constraints. So the basic idea about this method is to construct a new function that we call the Lagrangian, which is a combination of the original function and the constraint. So the Lagrangian is then differentiated with respect to the variables, and the resulting equations are solved by the optimal solution. So the Lagrangian is defined by this equation, L, function of x, y, and lambda, is equals to f of xy plus lambda g of xy. In this case, f is the function to be optimized, and g is the constraint function. Lambda here is the Lagrange multiplier. So we have an example. Suppose we want to optimize this function, f defined by y plus xy squared, subject to the constraint x minus y squared is equals to 1, using the method of Lagrange multiplier. So first we construct the Lagrangian. As I have said, this function L is defined as f of xy plus lambda times g of x comma y. G is the constraint, and f is the function that we need to optimize. So in our case, the function f is y plus xy squared, and g is given as x minus y squared is equals to 1, or even we can write x minus y squared minus 1 is equals to 0. So g is this function. So we can now differentiate L with respect to x partially. If we differentiate L partially with respect to x, we get y squared plus lambda. And differentiating L partially with respect to y, we get 1 plus 2xy minus 2y times lambda. So next, we equate this to derivative to 0 and solve the resulting equations. So we have the first derivative. If we equate this to 0, we get lambda squared plus y is equals to 0. Remember, a function is optimal at the point where the rate of change of the function is 0. So that's why we equate the derivative to 0. So from this equation, we can write lambda is equals to minus y squared, and then we substitute this here. So that from the second equation, once we equate this to 0, we shall substitute lambda is minus y squared. So we have, when we do that, we get 1 plus 2xy plus 2y cubed is 0. But we also have the constraint, x minus y squared is 1. So where we have x in this equation, we can make x the subject here to get 1 plus y squared, then substitute. So when we substitute and simplify, we get this equation. Equation solving, we get y is minus 0.38546. But remember, x is equals to 1 plus y squared. So we can substitute to get 1 plus minus 0.38546 raised to the power of 2. So this should give us the value of x, which is 1.14858. Those are the values of x and y at which the function f is optimal. Now, let's look at some application problems. One is where we can apply this method to optimize the utility function. So we have a utility function is a mathematical representation of the individual's preferences or satisfaction of a different choices of goods or services. So the utility function assigns a numerical value to each possible combination of goods or services, which represents the level of satisfaction or utility that the individual derives from consuming those goods or services. So the optimization of a utility function is a common problem in economics, and it is usually used to find the combination of goods or services that maximizes an individual's satisfaction subject to some certain constraints. And these constraints may include the budget constraint, for example. So the Lagrange method can be used to optimize a utility function by constructing a Lagrangian function that's a combination of the utility function and the constraint. We then differentiate with respect to the variables with the derivative to 0 and solve the resulting equations. So let's take an example. Suppose we consider the optimization problem of finding the combination of products A and B that would maximize the utility function given by u. A function of xy is equals to x squared plus y squared. In this expression, x denotes the quantity of a product A and y denotes the quantity of a product B, respectively. So this one has to be optimized or to be maximized subject to a budget constraint of $100. The unit price of product A is 10, while the unit price of product B is $20. So in this case, the problem is to determine the values of x and y. We should maximize the constraint u, subject to the fact that you only have $100. So we say that since each unit of A costs 20 shillings, or rather $10, and you need to purchase X units. Each unit of B costs $20, and you need to purchase Y units of them. then you see that the total cost of purchasing X units of A will be 10X, and the total cost of purchasing 20 units of B will be 20 times Y. So that when you purchase 20 Y units of B and X units of A, then the total cost incurred would be 10X plus 20Y. But remember, you only have $100, so this should not exceed 100, so this should be equals to $100. So this is the constraint function. This is the constraint function. So in this case, we can state our problem like we want to maximize the utility function, which is x squared plus y squared, subject to the constraint, which is 10x plus 20y is equals to 100. That is how we would state our problem. So the Lagrangian is given by now the function u plus lambda times the constraint. So we have x squared plus y squared plus lambda times 10x plus 20y minus 100. So we now differentiate this. Differentiating partially with respect to x, we get 2x plus 10 lambda. And when we differentiate partially with respect to y, we get 2y plus 20 lambda. So next, we equate the partial derivatives to 0. So from the first equation, this one, if we equate this to 0, that is 2x plus 10 lambda is equals to 0, then we can divide through by 2 to get x plus 5 lambda is equals to 0. The second equation, we can do the same. We get y plus 10 lambda is equals to 0. So we can get this equation and this one. And you see that from this equation, we can get x is minus 5 lambda. And from the second equation, this other one, we get y is equals to minus 10 lambda. The constraint was 10x plus 20y is equals to 100. If we substitute these two, that is, we replace x with minus 5 lambda and y with minus 10 lambda, then our equation is reduced to this, which we can solve to get lambda is minus 2 over 5. Then x becomes minus 5 times minus 2 over 5, which will give us 2, and y becomes minus 10 times minus 2 over 5, which is 4. So x is 2 and y is 4. That's the combination of goods that will maximize our utility function. Now we have a second example, which we can work out the same way. A man earns Kenya shillings 4,498 per week and spends his income on 3 products, A, B, and C. So the cost of purchasing these products are 20 for A, 35 for B, and 50 for C. So the respective function for the 3 products is given by u is equals to x squared plus 2y squared z, where x, y, and z denotes the quantities consumed for product A, B, and C respectively. The problem is to determine the quantity of each product that he should spend to maximize his utility. So the information we have here can be represented in a matrix form like this. The quantities, the items are A, B, and C. The quantities consumed are X, Y, and Z respectively. The unit price are given. So the total cost for the 3 is this, so that when he purchases X units of A at 20 shillings, Y units of B at 35 shillings, and Z units of C at 50 shillings each, then the total cost or the total amount incurred would be 20X plus that 5Y plus 50Z. And remember, this person earns 4,998. It is assumed that this man or this person spends all his money on the 3 products. So that this is the constraint function. So now the problem can therefore be stated as maximize U is equals to x squared plus 2y squared z, subject to 20x plus that 5y plus 50z is equals to 4998. So then we set up the Lagrangian. So we have the function here. Then this is the constraint function. We differentiate this partially with respect to x to get 2x plus 20 lambda, partially with respect to y to get 4yz plus that 5 lambda. And when we differentiate partially with respect to z, we get 2y squared plus 50 lambda. Now, to determine the optimal values, we equate each of these derivatives to 0 and then solve the resulting equation. So from here, we can write, from the first equation, we can get lambda is minus 1 over 10x. From the second equation here, we can get lambda, or rather from this equation, that equation, we can get lambda is equals to 2y squared all over 50 minus or even y squared over 25. From the second equation, this one, we can get lambda is equals to minus 4iz minus 4iz all over 35. So we can get that. So that by now equating this, for example, we can equate these two, or these two, or any two here. So if we equate these two, this and this, we get minus 1 over 10x is equals to minus 1 over 25 y squared, so that x becomes 2 over 5 y squared. And then when we equate 4, 5, and 6, these two, now we get this other equation from which z is equals to minus 7 over 20y. Now, once we have this equation and this one, remember we had the constraint, which was the equation we had up here, this equation. So we can substitute x and z so that we express x is 2 over 5y squared and z is 7 over 20y. So that our equation will be in terms of y. So this is reduced to a quadratic equation, and on solving we get y is approximately 21. Then we can substitute x. X is 2 over 5y squared, so when we substitute we get x is 176 and z is equals to 7. So that is how we can use the Lagrange method to optimize a function. Thank you for watching.